One of the tricky things about working with arrays is the fact you must know their size ahead of time. This is a problem for scenarios where adding and removing elements happens frequently, and space must be made for the new elements to be added. How can you provide a linear form of storage for scenarios like this? The answer to this is the usage of linked lists. In this video, I will discuss the most important aspects about the linked list data structure, which variations of it exist, and how can you implement them. Hi, my name is Ricardo Ferreira, and I'm a developer advocate here with AWS. Welcome back to this series about data structures. In this episode, I will talk about the linked list. This is one of the most deceptively simple data structures out there, as its implementation may look straightforward, but it forms the basis for a surprising number of questions during coding interviews. This happens because you can implement a linked list in about 10 minutes, and interviewers want to use the rest of the time for you to solve 2 or 3 problems. For a 1-hour coding interview session, this looks as a good usage of your time, as interviewers can extract more from you with a single data structure. Interviewers also love linked lists because it allows them to check your knowledge about pointers and references, as linked lists heavily relies on them. Moreover, linked lists offer a conveniently simple way to implement the backend storage of other data structures, such as queues, stacks, and hash tables. This means that knowing linked lists in intimate details grant you advantages with these other data structures. Let's take a look at linked lists at a greater level. So what is a linked list? A linked list is a collection of data elements that are connected together via links. Each data element in the collection includes a link to the next element, and some variations of the linked list data structure may also include a link to the previous element in the chain, allowing for efficient insertion and deletion of elements in the beginning, the middle, and in the end of the list. There are 3 most common variations of the linked list data structure, and each one of them may be particularly useful depending on the problem that you have to solve. For example, if you need to transverse the linked list only in the forward direction, which means starting reading from the head to the tail of the list, you can implement a singly linked list. With this type, each node has a reference to the next node only. Another variation is the doubly linked list. Each node has a reference to the next node and the previous node, allowing you to transverse the list both forward and backwards. Mind that both the singly and doubly linked lists allow you to transverse the list in the different directions, but don't allow you to quickly go back to the head or the tail of the list. If this is required, then you must implement the third type, which is called the circular linked list. With this type, each node has a reference to the next node and the previous node, and the list itself keeps track of the head and the tail during insertions and removals. As for what are the advantages of linked lists, they allow for quick manipulation of the data within the list, being a dynamic data structure that can grow and shrink in size at runtime by allocating and deallocating memory. As a result, there is no need to specify the linked list initial size. There is no memory wastage in the linked list since the size of the linked list increases or decreases at runtime. The linked list makes it easier to insert and delete elements. After an element is inserted or deleted, there is no need to move it. Only the address in the next pointer or perhaps the previous pointers needs to be updated. Just like any other data structure, linked lists also have disadvantages. For instance, they require more memory than an array, because a reference is necessary to store the address of the next entry or the previous entry in the linked list. And all of this consumes additional memory, as a node is a combination of its data and its references. Finding a single element is much harder since there is no index pointing to the element. Therefore, there is no random access to the elements. You always need to transverse the list if you want to find one single element. Also, unlike arrays, linked lists provide no memory locality. Using linked lists brings many performance disadvantages, as you cannot exploit the processor speed and its direct access to cache. All right, enough with the theory. Let's now learn how to implement a linked list and review some of the problems that you may have to solve during your coding interview. All right, let's start the most exciting part of this episode, which is the coding part. Back to our Visual Studio Code, we're going to start implementation of our linked list. We're going to start with a singly one. So I'm going to ask CodeWhisperer to implement a singly linked list, period. All right, let's see. I'm going to hit enter, see what happens next. And then sometimes you're going to notice that CodeWhisperer won't recommend nothing for you, but what this means is that you might need to provide some hints about where you want the code to be generated. For example, here, I'm not within any declaration of a class or any method, so it doesn't know what to do, right? So a linked list is usually going to be a combination of at least two classes, right? The actual linked list and a class that represents the node. So I am going to actually invoke CodeWhisperer here besides the declaration of the linked list. And then as you can see here, is starting to kind of, oh, okay, you need a node for the linked list, right? So yes, I need a node. And just like it's recommending here, this node needs to contain data and a reference or pointer, right, to the next element. So far so good. I'm going to start hitting enter, and here's a very interesting constructor for us to initialize the data. Another enter. No, I don't want a pointer to the next node. What is going to be really useful here in this class is maybe some methods to retrieve the next element. So maybe I could provide a hint. One for retrieving the data. I think this is important. I think this is good. But if I hit enter again, what I want is to set the data. Okay, I'll deal with it. But what I need, CodeWhisperer, yes, that's what I need. It's a method to retrieve the reference of the next node. And for the sake of the argument, one also to write the next reference. So I think now we're starting to look good. One thing that I'm going to do before proceeding is that I'm going to refactor the name of this class to maybe node element. I think that's going to be a node element, because I want to avoid in future episodes when we start like playing with CodeWhisperer, clashes of CodeWhisperer also recommending another class called node. So for this particular case, we're going to deal with the node element, right? So for CodeWhisperer, it knows how to keep track of all the existing classes, so it won't make any difference, right? So now that we have a node, and let's recap, this node contains the data and the reference to the next element, and everything else is just plain old Pojo and Java to expose the internal attributes to the outside world, right? So with the proper visibility modifiers. So now we can go back to our linked list class. And then if we put here and ask CodeWhisperer, I can always hit Option C. You're going to see that it's starting to suggest some things for us here. Now, what it's suggesting here is essentially what seems to be what we are going to accomplish later, which is evolve from the singly linked list to a doubly one, because as you can see here, it's keeping track of the head and the tail. Actually, it's suggesting the use of a circular one, but I'm going to accept it and modify the data a little bit, because at this point, I don't want, let me close this method declaration here. At this point, I don't want to, okay, let me close this. And then the definition of the node elements was created outside the declaration of the class. So maybe I need to close this class here first. Okay. And then I'm going to put the node elements below. So now the compiler is understanding better the code. So back to what we were saying before, we don't want the usage of the head and tail, only the head actually for now, because a singly linked list needs to have the reference, needs to keep track of the head first, and I'm going to remove everything that has to do with the tail. So one interesting thing that you can do with CodeWhisperer when this situation happens, which means you accept something but you don't want all of the code, you can always literally remove everything generated, and if you hit enter again, it's going to suggest based on the current shape of your implementation. So now, as you can see here, it's only recommending things that match with what you have, which is keep track of the head and keep track of the size, right? I'm going to do the same thing for the get here. Actually, I'm going to remove this method get. We won't need any get to retrieve a specific element, at least not for now. And I'm going to remove the method remove. It sounds redundant, but it isn't. Okay, so with that done, let's solve this. Okay, size is not being used because we're not exposing to the outside world. So maybe what we can do is to use, so let's create a method to retrieve the size of this list. Now let's recap what we have done. First of all, you've declared a class that represents the node. A node contains the data and the next element, and then the exposing to the outside world. And then the actual linked list, the primary job is to keep track of the head, right? And then, which means that every time you're gonna add some data in, not only you have to provide a code that's gonna do this, but it needs to keep updating the head to always keep track of what is the beginning of the list, right? And then a method to retrieve the size. For us to check if it's working, let's create the famous method to print the list. So maybe create a method. Okay. Code Whisperer is getting used to the way I think, so it's suggesting exactly what I know. So I'm going to hit enter. I'm going to accept the implementation of it. Okay. Maybe I have to finish this here, and then something else needs to be, no, this. Is that correct? Retrieve the current element, which is starting for the head, and then while it's transversing the list, it means the current elements are different than null, is printing the current one and then retrieving the next one, which is going to be the current one. Seems to be all right. Let's test it out. So let's create a main method to this. So main method. All right. So let's add 3 elements to this list, and then let's ask the list to print the elements. I think we're good here. So we've instantiated the linked list. We've added 3 elements, 1, 2, 3, and then we're going to print the list. So let's see how this goes. I'm going to click run. Actually, click it twice, but doesn't matter. I can remove one of the consoles. This one's going to be fine. So let's click again. Yeah, 1, 2, 3. So it's printing the list, and matter that we are actually printing the list transversing forward direction, right? Which start from the head, and then we are iterating over the existing elements of the list. So it seems to be working correct, right? Now, one of the problems that you might probably see in coding interviews is the transformation of a singly linked list to a doubly one, right? So the main purpose of this type of questions for the interviewer perspective is for them to evaluate and measure your knowledge in terms, do you really know the internal structure of a linked list, right? So in this case, what is a doubly linked list? Is a one that where each element contains a reference to the next element and the previous element. So for our implementation here, what we need to do is to create another reference to a node element that's going to represent the previous, right? The previous element. So most of the time, Code Whisperer, if you think press enter here, is going to try to suggest this. But if not, you can always implement yourself. So like node element, yeah, here we go. So it's starting to know what I'm intending to do. It's predicting my intention. So yes, I need a previous one, exactly. And because of this, I need also to create a blank constructor. Yeah, probably we need it. It's always a best practice. But more than this, we also need a way for us to expose, just like we did here, with the getters and the setters to the next pointer. So I'm going to hit enter here. Here we go. I need a getter for the previous, and I need a setter from the previous. So that sounds more like it. And here's the interesting part. now that we've updated our node element, right? So that's the first step when creating a doubly linked list. You need to, in the class or the implementation that you have for the node, you have to have those two references or pointers. But the job is not done. You also have to update your implementation of the linked list, because remember, everything about the linked list is keeping tracking of the head, right? Because now, even if you move backward or forward, you need to also keep track of this. And during the insertion time, which is this method here, add, you also need to update the information about the previous, or we call it previous, previous element. So again, what you can always do with Code Whisperer is literally remove all the implementation that currently is only providing awareness of the next one. So you can remove, and then if you hit enter again, it's going to provide you a new suggestion that takes into the consideration the prev and the next one. So as you can see here, yep, that's it. So I'm gonna accept it. So as you can see here now, not only is updating the references to the next element, but for the previous element as well, right? We don't need to update the print. The print is basically moving forward. So it's good. The only thing I'm going to do here to test if this is double linked list is working is to create a new method that's going to do the printing, but printing in reverse. Meaning it's going to the end of the list and then it's going to print back forward, right? So it's the proof that it is able to retrieve the previous elements once given a current element of the list. So I am going to create a method to print the list in reverse order, which by itself, it's another problem that you might see in your interview. Not exactly with this name, but again, is the interviewee wanting to know if you understand the structure of a singly or a doubly linked list. So let's see how this goes. Print reverse, okay, start with the head, right? And then let's see how this goes again. And then it's going to basically iterate over the entire linked list. Pay attention to this, because this, depending on the size of this linked list, this might be time consuming. And then here you go. Once you transverse the entire list, meaning you're going to reach the last element of the list. So now you are doing the operation, the inverse operation, which is going back, right? So you just move forward. Now we're moving in reverse. And then you are printing all the data that's currently existing. So in order to prove that theory, we're going to include another method call here after list print. Actually, let's do the famous separation here so we can see the difference. And then list dot print and reverse. Let's see if this works. So I'm going to click run. And it works. As you can see here, it prints 1, 2, 3, which are the elements that have been added, and then 3, 2, 1, which is start from the end. It printed in reverse. So that proves that not only using a double linked list, you can move in different directions, but also it proves to the interviewer that you know the structure of a singly and a double linked list. This is very important because this is what they want to measure on you if you have complete awareness about how to implement a linked list. Now let's do a similar exercise with my reminds a similar problem, which is how to transform a doubly linked list, or for the sake of the argument, a singly linked list, to a circular one, right? So a circular linked list is one that keeps track of the head of the linked list as well as of the tail of the linked list, which is exactly what Code Whisperer whispered in the beginning, and we didn't accept it whatsoever. But now we're going to accept the recommendation. So the first step is to make sure that you have everything implemented for the node perspective. So for the node perspective, since we want a doubly one, everything is in place, so you don't need to change much in here. And then we're also need to keep track of the, I'm going to hit enter here and see what Code Whisperer suggests, but if it doesn't suggest anything, we can give a hint about our intention, which is, hey, Code Whisperer, could you, yes, here we go. Could you create a tail reference for me? Yes, that's what I want. I need a tail. And now we need to not only modify the constructor, because we need to initialize with, actually, for the Java perspective, we don't actually need to do this. This is more like a best practice, but by default, references in Java are initialized with null, and primitive types are initialized with 0, in this case of integer. But anyway, just for the sake of completeness, let's accept the recommendation. And then we also need to literally replace the entire implementation of the add method. So just like we did before, let's remove and delete everything. And you can always ask Code Whisperer to do your job again. So now consider that not only you have to keep track of the head, you have to keep track of the tail. So let's see what Code Whisperer is preparing for us. It's spinning here, as you can see here on the bottom. Nothing yet, so let's ask again, Option C. All right, now we have some suggestions. Let's whatever the suggestion had. Yes, so now, as you can see here, the implementation is keeping track of the heads and the tails, right? And all right, so every time you add a new element, it's going to keep updating those two references here. So every time you need it, you always have a reference of the current head and the current tail every time you add a new element, because it's dynamic, right? In order for us to validate this, we're going to use, well, first of all, let's run the code one more time. It needs to continue doing what it's supposed to do. So printing 1, 2, 3 and printing 3, 2, 1. So it's doing what it's supposed to do. But in order for us to validate if the usage of a tail is actually impacting in the potential algorithms that you can write, which is the main characteristics of using a circular linked list, because you can always count with, all right, I have a reference to the end, and then I can go back to the beginning. Because if you recall, the print reverse, what it's currently doing, once it was implemented as a double linked list, was to transversing at least first the linked list to go to the end, and then once in the end, it was going back to the head, right, which is the backwards direction. So let's do this. Now that we have a tail reference, let's remove this implementation, and let's see if the new implementation suggests something more efficient, because before it was doing like a two transversion of the list, and this can be dangerous, as we recall, if you have multiple elements. So I'm going to hit enter and ask Code Whisperer to provide a new implementation. And as you can see here, the implementation is already paying off, because look, you have basically a reference to the tail, which is the reference that is being kept trapped inside the linked list data directory. And then we're doing only one transverse of the list, which is backwards. So we have the tail, and then we can go back to the head, to the beginning, using one while loop. So with that change, let's see if the behavior didn't change, right? Only it's more efficient, right? So I'm going to run the code again, and let's see if it's continuing to print and generating the expected output. And it is like 1, 2, 3, which is the elements, and 3, 2, 1, which is the reverse order. But now, what is the difference? It's because the usage of a circular linked list allows a more efficient algorithm to transverse back and forth. Like that's the beauty. That's what you have to have in mind while implement these data structures. Very cool, right? So let's leverage another characteristics of circular linked lists, which is how easy it can be to insert a new element, but in the middle of the list, right? If you recall, when we are dealing with arrays, inserting an element in the middle of the list was relatively easy, because arrays has the notion of indexes, so we can kind of easy calculate where is the middle of the array. But with linked list, you don't have this concept of indexes, right? So how you can actually going to do the whole, I want to insert in the middle. So let's see how this goes, which, by the way, is another very common problem in common coding interviews, which is how to add elements into the middle of the linked list. So let's ask Code Whisperer to create a method to remove, no, to insert a new element in the middle of the list. All right, So let's be very specific about what we expect from Code Whisperer. I'm going to hit enter, and then the method signature is not ideal at this point because I don't want to have to specify the index because this is not an array. So for a situation like this, we can always like start with the method signature ourselves, which is void insert, and then accept but not the position, only the data, right? So we can do this and then close the method declaration, and then let's Code Whisperer do the rest. There are some suggestions here. Let's see which one has a more efficient way to do things. Let's review the first. It creates the new element with the new data, of course, start from the head, and then transverse the list, and then basically no, this is not what we want. This is basically a plain old adding an element in the list. So let's go to the other one. Create the element. If the head is new, blah, blah, blah. If not, basically do what was doing before and then update the cell. This is not what we want. In this one, we have head is new, blah, 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 else, node elements, start with I, and then is basically comparing, sounds more interesting. It's basically calculating, given the size, because you know that every time you add a new element, the size is updated, right? There's an internal attribute that holds that information. So it's comparing where is the size, if divided by 2 is the middle, and then that's where the new element is going to be set. And then basically do the whole pointing, referencing, and dereferences to the previous and the next one. And let's just check the last one to see if it's more intelligent. Current new, blah, blah, blah. No. So our winner is this one. So let's use this one. And then for us to see if this is working, we need to create another method that retrieves what is the element that's currently stored in the middle of the linked list. So this is going to be a new method. So we're going to create a method that retrieves the element in the middle of the list. All right, so let's see how this goes. Get middle. I like the signature. This is exactly what we need. And returns an integer. Okay, and then is basically let's review the code. Start with the head, have a counter here, I, and then start counting until it measure if it's the middle, and then when it hits the middle, retrieves the current, and then return the data. That means that is going to transverse the linked list at least half of the linked list, right? So regardless of the number of elements, that may take a while. If it has 100 elements, it's going to transfer at least 50 elements of it. So you have to keep this in mind, right? But anyway, the algorithm seems correct. Well, let's test it out. So now that we have, let's remove this. We know that printing in reverse is working. So we're going to add the 3 numbers, print them, and then we're going to we're going to insert the one in the middle, last list. So add, what is the method signature that we've created for this? Insert data, print reverse. I forgot what is the method. Public void insert. We have 2 inserts right now. One is add and another one is insert. All right, so the one we have to use is insert. So let's insert the lucky number 14, right? If you haven't watched the series from the beginning, you might have noticed that I have a history about the number 14. If you were curious about this, put here in the comments if you want to hear the story about it, and I will gladly answer for it. So we're going to insert the number 14, and then we're going to print number in the middle, which is, yeah, that's what I need. Thank you, Code Whisperer. Almost like you're doing more than I needed, but yes, we're going to print it, insert in the middle, and then we're going to printed value. I'm not very comfortable with the method signature insert because it's a little misleading for our purposes. So I'm going to refactor this method to something more descriptive. So add element to middle, something more descriptive, right? So now we have more control about our intentions in the code. All right, let's see if this is working. So let's do another print here in between one print and the other, so we can see more the details. Print. Yeah, so let's run this code and see how this goes. All right, let's recap the output. This is the result of the first print. 1, 2, 3, no big deal. And then after this, we've asked it to insert number 14 in the middle. So 1, 2, the middle is here, 3. Kind of makes sense, okay? And then number in the middle is 14. So the algorithm is doing what it's supposed to do. If we recap the implementation, so basically to retrieve in the middle of the element, the list, or to add in the middle, you have to calculate and keep track of where is the middle. So you always going to have some sort of a counter, and then you have to transverse the list to kind of compare this counter to where is actually reaching the middle of the list. And that reminds me that I forgot to raise your attention to this very interesting element that CodeWhisperer generated for us, and we didn't pay attention to it, which is the concept of size, right? So every time you add or remove elements from the linked list, you have to keep updating the size. If further you want to do things like keeping tracking where is the middle, where is the 75% of the list, things like this. So don't forget to keep track, besides like keeping track of the head and the tail, right? So let's take a look at how we can do some sort of a sorting in the linked list. To play with some sorting, the first thing we need to do is to include a method in our implementation to create some random values that we could play with. So I'm going to ask CodeWhisperer to create. You have noticed that every time I'm going to type up create, I always misspell it and I have to go back and fix it. So I have to take care of this. A method to add random values to the list given a number of elements to be provided as a parameter. So I think that's a very suggestive prompt for our CodeWhisperer. So let's hit enter. And then the implementation seems to be doing what it's supposed to. Let's review the code. Add random values. We'll specify the number of elements to be added. It's going to iterate over these elements. And then for each one of them, it's going to create a random value. And then call the method add, which, mind you, that it is the method that we have implemented before. So this is one of the interesting things that you have to be aware about CodeWhisperer. And one of the nice things it does, which is the awareness of the existing code base you provide with. So if you have your existing implementation, open a tab, and you have multiple other tabs with other classes or implement part of your code, all of this is going to build up for CodeWhisperer to build a proper prompt that's going to be passed over to the generative AI backend. So all of this will sum up in for CodeWhisperer to provide with a better recommendation. In this case, as you can see here, it's leveraging the existing methods available. So this is pretty awesome if you think about how you could expect CodeWhisperer to suggest something that already exists and not just create random things out of nothing. Now that we have this method available, let's use it. So after creating our list, we're going to list.add random values. Let's add 3 for now. And then let's print the list to see if those numbers are indeed random. So I'm going to click run. And let's review the code. 89, 41, 96. Yeah, they seem random to me, right? Let's actually do something before we move forward. Let's use debug visualizer so we can inspect the structure of our linked list, and so you can see how does it look like in memory. So I'm going to put a breakpoint here on print, and then instead of clicking on run, I'm going to click debug. So debug, the code is waiting to be executed on list print. So I'm going to select our linked list and invoke debug visualizer using selection as expression. So this is our linked list, mind you. And although I'm sure that it's pretty hard for you to look as of now because the diagram is huge, right? But here is what you have to keep in mind. First of all, this is the root of our implementation. So our implementation has a current size of 3. Makes sense because we have added 3 elements. And then it has a pointer to the tail and a pointer to the head. If we move to the head, it's going to be the first element whose data is 71. Let's see if this is true. So if we print the execution, so yeah, first element 71, second element 49. So let's see if this adds up. So this is our linked list. First element, the data is 42. No, actually, this is the tail. So we're looking to the tail, which makes sense. Yeah, the tail is 42. If we look this and look to the head's going to be the number 71. Makes sense. Here you go. And then since it's the head of the linked list, it has no previous. So makes sense, it's new, but it has a next element. So if we move to the next element, the next element is going to have the data 49. So it matches what we are seeing here on the output. So the thing that you have to keep in mind, I'm going to zoom out a bit, is that this is the structure created in memory for a linked list implementation with only 3 elements. Now imagine the amount of references and pointers and links that would be created if you had 10,000 elements on this list. So this is what I meant when I said before that linked list consumes more memory. All of those references needs to be materialized on heap, on a JVM, in case of Java, of course, so they can sustain those references and pointers to all over the place. So keep that in mind, because if the problem that you are trying to solve is leaning towards more like optimizing in terms of memory consumption, you have to remember that, oh yeah, linked lists are very hungry in terms of memory consumption, so I have to avoid them as much as possible. Or perhaps trade off the usage of a circular linked list for a doubly or maybe a singly, because a singly is going to use less references than a doubly or a circular linked list. So just keep that in mind. I'm going to finish the debug visualizer, so it's generating the random net numbers that we've needed. So let's play with the sorting right now. So I'm going to ask Code Whisperer to create a method. Now the create was spelled properly. Create a method to sort the list. Just this. Let's see how what comes from this suggestion. So sort, and then I'm going to accept. And giving the implementation, we can almost figure it out what algorithm is being suggested here. I would bet that this looks like a bubble sort, right? Because remember, the bubble sort algorithm has this kind of outer loop. It's going to retrieve the head, start from the beginning. The outer loop for each iteration is going to retrieve the current element, and then it's going to have an inner loop that's going to walk over the implementation, retrieve the current data, set the current data, blah, 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 and move to the next one, right? So it's basically do the whole swapping in the inner loop, and then it's going to transverse all the entire list, which can be dangerous if that list is big, right? So this is one of the things that you have to keep in mind also. If you have to end up doing some sort of a sorting, always make sure to clarify with the interviewer. Okay, are we dealing here with like a list of 3 elements like here, or we're dealing with a list of 10,000 elements? Because depending on the size, better sorting algorithms could be used, such as like the merge sort or the quick sort, right? So just keep that in mind. But I think bubble sort for our purposes here is gonna suit our needs. Let's just change our main method quickly here to, after we print, we're going to put a separator here so we can see the difference for the unsorted version and the sorted version. And then we're going to ask the list to be sorted. And then we're going to print one more time. So this print is going to print all the numbers unsorted. We have a separator. We're gonna sort in place sorting, right? We're gonna like do the whole like rearranging of the elements in memory, and then we're gonna print the current state of it. To make things more interesting, instead of only dealing with 3 elements, let's add 10 elements. I think 10 elements is going to be more like, useful for our purposes here of testing the sorting. Sounds okay. I'm gonna click run and check if this is doing what it's supposed to do. So this is our list printed unsorted, clearly with random values, and this is our list with a sorted version. Let's see if the sorting makes sense. 3, 4, 6, 19, 29, 49, 55, 66, 68, 89. Yeah, seems to be correct. And these are 10 numbers. So our sorting is working as expected. So just to recap, when you have to do some sort of a sorting operation of a linked list, you're always going to do either start from the head, or perhaps if you have working with a circular linked list, you can start with the tail. But regardless, you are going to kind of iterate over, instead of using counters and accessing the indices of a given element, just like we did with arrays, you are actually going to retrieve the references and then keep using the next or previous elements to do the whole, like moving forward or backward, right? So that is the fundamental difference that you have to keep in mind, regardless of the algorithm that you are going to use. In this case, we're using bubble sort, but mind you that if we had used it like quicksort, for example, the quicksort is basically an algorithm that does the whole, break it into multiple halves. It calculates a partition, the middle of your list. So you have to navigate at least the middle of your list and calculate the partition, and then break it out and do some sort of a recursion to sort one piece, sort another, and then merge back, right? So basically this is how quicksort works. But regardless, you have to remember that when you navigate through the list, now you are relying on references, and that's what you have to do to move forward and backward. All right. Let's wrap up what you have seen in this episode. A linked list is a collection of data elements connected together via links. There are 3 common variations of a linked list: singly, doubly, and circular linked lists. Linked lists allow for quick manipulation of data, dynamic size growth and shrinking, and there is no memory wastage. However, they require more memory than when compared to arrays, and finding a single element is much harder, as they provide no random access to any one of the elements. My suggestion for you is to keep practicing different problems related to linked lists, and use Amazon Code Whisperer to assist you with the code generation. Then, spend some time studying the generated code, and whenever applicable, criticize and correct the code. In the next episode of this series, we will take a look at the queue data structure. If you start watching this series from the playlist, the next video about queues should start pretty soon. That reminds me, the playlist from YouTube is essentially a linked list, right? A singly one, because each video contains a reference to the next one. If you haven't started watching the series from the playlist, don't worry. I put the link of the next video about queues in the description below. See you in a bit.